Phase diagrams provide insights into the microstructure of materials, especially how different phases come together at various compositions and temperatures. To determine the proportion of phases in a two-phase region, we use a method called the lever rule. Consider a binary isomorphous phase diagram for two ceramics, forsterite, Mg2CO4, and phyolite, Fe2CO4. Both have the olivine crystal structure but differ in their cations, Mg superscript 2 and Fe superscript 2, respectively. These two ceramics exhibit complete solid solubility. As an example, let's cool down a 50-50 mixture of these two ceramics. The first solid forms at a specific temperature, and the phase diagram helps determine the composition of the solid and liquid phases at each temperature. For instance, at a particular point, the composition of the solid might be around 20% phyolite and 80% forsterite. To calculate how much of each phase, solid, olivine, and liquid, is present, the lever rule is applied. Total length of the line. First, find the distance between the two compositions on the phase diagram. Phase fraction calculation. The fraction of each phase is found by dividing the segment lengths on the diagram. For example, the fraction of solid olivine is determined by dividing the length of the line segment corresponding to liquid composition by the total line length. Using this method, we can calculate the weight fraction of each phase. For example, if the weight fraction of olivine is 63.6%, the remaining fraction is liquid, 36.4%. The lever rule ensures accurate calculation of phase proportions and can be applied in weight percent or atomic percent, depending on the type of diagram.